All right, you guys, this is our kind of second attempt on some accumulation problems. So remember, if we would have had a Saturday study session, we would have done like a whole session on this. And sometimes like I do it again just for the Junction kids because it's just kind of like not truly taught in our book and you don't really get any practice on it like we do a lot of other things. And I mean, I know like AP particular problems are harder just in their own right, but then like if you haven't even done this at like a small like chapter unit test, then it's really hard. But I think you can get the hang of them if you keep truly watching the videos, trying it on your own. So you should try this problem on your own, then watch the video of how to do it, then do your one on homework and go back and watch the homework video when it's public after a couple days so you can see how you did and why you would get the score that you got out of 9. So this is a calculator active problem, right? It's number 2. Problems 1 and 2 are calculator active. Problems 3 through 6 are non-calculator problems. So typically with accumulation problems, we just like name them by what they're about. So this is the Sandy Beach problem. It's way back from the year 2005. And actually when I do that accumulation session for Saturday study sessions, I always start with this problem. I feel like it kind of like covers the basis of accumulation in a good way. And because it is kind of like a ways back, it's like an easier one a little bit sometimes to get started with. And it shows a lot of kids who aren't very good with the use of their calculator, how to use their calculator. Because a lot of other schools, I don't think like teach the calculator as much as we do. So you definitely need to have your calculators out for this problem. And there will be like a lot of calculator stuff we go through and review. So remember, if it's calculator active and you're doing anything, a lot of times it's like setup of an integral and then you math 9, right? So the stem of the problem says, the tide removes sand from the Sandy Point beach, I just totally flipped those words around, at a rate modeled by the function r given by r of t equals 2 plus 5 times sine of 4 pi t over 25. So I wrote that rule up on the board. But notice it says it's a rate. Just because it doesn't have a prime doesn't mean it can't be a rate of change. And this is what the tide is removing the sand off the beach for. So that's probably why they're using r of t. But even if the letter kind of gives it away, I would like be really distinct on my work. And I would say, okay, this is the one that's removing the sand. Right? And then we keep reading, and then there's this pumping station. Hernie, did you know that there was a station to pump sand on a beach? Because I certainly did not. A pumping station adds sand to the beach. So this is the adding sand.
Yeah, have you never been to a beach before? That's not every
has
beach.
A pumping station? The pumping station adds sand to the beach at a rate modeled by the function s, and the function s is given by s of t equals 15t over 1 plus 3t. And then we keep reading, and it says both r of t and s of t have units of cubic yards per hour. So that already should have given it away, even if they didn't specifically say this is a rate and this one's a rate, that it would be a rate of change, right? Because we have these cubic yards per hour, and it says both of them are cubic yards per hour. Okay, so something with respect to time, that's going to be a derivative. And t is measured in hours from 0 is less than or equal to t, which is less than or equal to 6. So they're giving us the time in interval notation if you want to put it in, or they're giving us the time in inequality notation. If you want to put it in interval notation, that's fine. And it says like both of these are happening. And that's not always the case, especially as like the years have gotten closer to where we are now. Sometimes what's happening as the rate in and the rate out are for different time frames. But for this one, our sand is being removed constantly and being added in by the pumping station for the times 0 to 6. And we're including those endpoints. And it's going to still be measured in hours. And then we keep reading and it says at time t equals 0, the beach contains 2,500 cubic yards of sand. So that sounds to me like, oh, I don't know, an initial condition. So this is our time. And this isn't the rate of the removing sand, and this is not the rate of the adding sand. This is like the amount of sand. So sometimes I'll just put, well, maybe I don't know what the letter is, but this is just the cubic yards of sand, where this is my time in hours. And maybe like later I might establish my own letter for that. A lot of times I use A of t to stand for the amount. Okay, the amount of whatever I have with these two rates of change, rate coming in and rate change going out. So this is a part A through D problem, which means not any one part's going to be probably super, super heavy. I mean, you definitely want to try all parts, but if you don't get a part, like don't panic. We're really not expecting you to get 9 out of 9. We're expecting you to get like 4 to 6 out of 9 on most problems, hopefully with watching the videos and get better and get better and get better. So part A says, how much sand will the tide remove from the beach during this 6-hour period? Indicate units of measure. So if they're asking for units of measure, that means that's going to be a point. in our points for part A. So if they're just asking us how much sand will be removed, we don't care about the stuff that's coming in. We don't care about what we start with. The initial condition has nothing to do with this, because if we just care about the stuff being removed from the whole time frame, 0 to 6, don't we just want to take the rate of change of the removing sand? It doesn't matter that it doesn't have a prime on it. It's still the rate of change. If we accumulate R of t with respect to time from 0 to 6, isn't that going to give us the amount that's removed over that 6-hour time period? So I didn't write this down yet, but Mr. Harney did go ahead and put that rule in for Y1. And I'm going to go ahead and have him show you that, because it's harder, right? You have to be in radians. You have to make sure that I would do this in pretty print. You got to get your pi on there. So this would be the rule that you want to store in Y1, and definitely write down which one you store where. I just wrote them down in order, right? And then the other fraction, we still did vertically up and down. Our t's are like our x's. That's the adding sand rate of change, and that's what we stored in Y2. But the only one we care about right now is Y1. So Mr. Herney, to 3 decimal places, what'd you get for that one?
31.816.
And then because they particularly asked us if we are doing the definite integral of our rate of removing sand in yards per hour, wouldn't we just get back yards of sand, cubic yards? And I'm going to even be more distinct. That would be the cubic yards of sand over the 6 hours, or 6-hour interval, or the first 6 hours, or from time t equals 0 to time t equals 6. I mean, there's a million ways to say that are all acceptable ways to say that. So remember, it's calculator active. We're not trying to integrate anything by hand. Like, are you crazy, you guys? You're not integrating by hand right here. Like you are doing Math 9, calculator active problem. And because it was only asking us about the sand that was being removed, that's why we only used that rate of change for the removing sand. Part B, write an expression for y of t, the total number of cubic yards of sand on the beach at time t. Okay, so if they didn't tell me to use y of t, I probably would have used a of t, the amount of cubic yards of sand according to any time. But they're particularly telling us to use y of t. So this is like our initial condition of the yards, cubic yards of sand at time 0. So that's like our y of t. So we're writing like a general rule, right? So this, to me, is that twist on fundamental thermocalculus, which it's hard because it's all letters, and the letters are like a little bit like hard to know how to deal with. But if I want to find the cubic yards of sand according to any time, I got to take my initial yards at time 0, so y of 0, plus my antiderivative. Well, this lower boundary has to be matching. Oh, from time 0 to this upper time t, right? Because we don't know what time. We're writing it in general of time t on top. But then, you guys, this can't be t's down here because this is already t. So that's the part that's like a little bit tricky. But I think that they're fairly lenient. Like if you have t and it's supposed to be a different letter, and they'll just go, well, kind of looks like an x. But don't we have like sand that's coming in and sand that's going out from the tide? We have this rate in and rate out. And if that hasn't clicked into your brain yet on accumulation, that's the idea. That if you're finding at the end the amount of stuff, whatever the amount of stuff is, in this case it's cubic yards of sand, you're going to have to worry about the rate in minus the rate out. And you're going to have to integrate that. And sometimes they're over different time frames. In this case, it's the same. This was always happening the same way for both the stuff coming in and out from time 0 to 6, or any time frame between 0 and 6. So I would say, okay, it's got to be the stuff coming in, right? We got to add the stuff coming in. That's from the pumping station. That's probably why they used S of, and I'm not using T, I'm using X because it can't be T. So eventually, like, this T would go in here. Minus the sand being removed, R of X. And then the dx on the end to show integrating both of those things. Right? Calculus is beautiful, so we want to integrate both of these things with respect to X. If you broke it up, then that would be okay too. And no matter what, I probably would start with that line, and then to me that like gets that twist of fundamental theorem of my calculus in my head. Oh, this is time 0, this has to be 0, this is the final time, this has to be the final time on the upper boundary. And then I would go ahead and plug in the 2500 because that we knew for the initial condition. So if you want to find the total amount after a certain time frame, the initial condition is considered. If you just want to know the sand coming in or the sand coming out, that doesn't have anything to do with the initial condition. So 2500 plus the definite integral from 0 to t And I could leave this S of x minus R of x all with respect to x, or you could say, oh, S of x by itself with respect to x, because that would be the sand coming in, minus the antiderivative from 0 to t of R of x dx, because that would be the sand being removed from the tide. Either one is fine. They're both like full credit. But the idea is, if this is t, this can't be t, which I know is a little bit tricky. And that's all they wanted on part B, like the general rule to get the cubic yards of sand on the beach according to any time. Okay? So that means we're on to C. So part C says, find the rate at which the total amount of sand on the beach is changing at time t. So if we want to find the rate, we want to find a rate of change of the total amount of sand, how it's changing at time t equals 4. Oh, so don't we really want to consider like the rate coming in minus the rate going out at time t equals 4. So the rate going in was the sand being pumped, S of 4, minus the rate going out was the sand being removed from the tide, R of 4. And then I just want to do, this is really in Y2, Y2 of 4 on a home screen, minus this is in Y1, Y1 of 4 on a home screen, and figure out what that answer is. And isn't that going to be representing the rate of change of the amount of sand at time 4? So we get negative 1.909. And this would be the same units as what R and S originally were at the beginning, which were cubic yards per hour. Now, they don't ask for this. They really just ask for this answer. But just for kicks and giggles, and because it's a harder thing to get points on, I think we should try interpreting this in context. So they do often ask you, once you find a derivative, to interpret it in context of the problem. So maybe just add on this problem like a little extra bit of notes. It just won't be anything that we award points to because I'm just like adding it in, right? Extra Miss Ryan bonus points. So if I said, okay, interpret what that means in context of this problem, wouldn't you say the amount of sand on the beach is, oh, I got a negative derivative, so I would say is decreasing at a rate, I mean, we found a rate of change, so say at a rate of, but remember, if we've already used the word decreasing, since we have a negative derivative, we don't put the negative on the number. We say decreasing at a positive amount at a rate of approximately 1.909. We would definitely have to have cubic yards per hour, the units to match a rate of change, at t equals 4 hours. Or 4 hours into the 0 to 6 hour time frame, or whatever. I would just say at t equals 4 hours. So if you're interpreting a derivative, they're looking for those three things. Some word that matches the sign that you got for your derivative numerical value, that you have the correct units for your rate of change, and that you restate the time. And if all three of those things aren't there, you wouldn't get the points. Okay? So they didn't really ask for that, but I think it's just a good review. They might ask you for that on your homework problem, and maybe that will help some of you on your homework problem to remember how to interpret a derivative. We also have done a problem on one of our free responses in the past where we ended up finding, it was kind of similar to this, but we ended up finding a rate of a rate. So we were like taking a first derivative rule and taking the derivative of it at a certain time. So it was like something per time squared. It was the rate of the rate. It was interesting. Which of course is like an upscale problem, and sometimes that's why you don't get all the points out of 9. That's pretty impossible. Most of the time we're just hoping that you can scavenge up somewhere between 4 and 6, and if you're doing that consistently, you should do okay. So part D, last part, says 4 zeros less than or equal to t, which is less than or equal to 6. At what time t is the amount of sand on the beach a minimum, and what is the minimum value? Justify your answers. So if they're asking us at what time we reach a minimum, what's the minimum amount of sand, isn't that really asking for an absolute or a global minimum? So if we're talking about absolute or global extrema, aren't we thinking, oh, extreme value theorem, EVT. So EVT is where we want to figure out our potential candidates to test. This is the best way to try and show the extreme value theorem. You list out your candidates, you test them using the candidates test, and then you come up with your conclusion. So we know we need to test time t equals 0 and t equals 6, because those are our endpoints. Plus they restated those in part D's directions, right? So we know that we got to test our endpoints. You just have to be continuous for EBT to apply, and these are going to be fine. These are going to be values that are defined everywhere except negative 1/3, and that's not even in our time from 0 to 6, so like we're fine. For differentiable everywhere, we're going to be continuous. And then we also need to find where the derivative equals 0, and if we're looking for absolute min, at least it's got to be a local min. So don't we also need the sign of the derivative to switch the correct way, which means it needs to switch from negative to positive to be having the original function go from decreasing to increasing to have like a minimum low valley. But it's kind of tricky because you have this stuff about the rate coming in and the rate going out. So they asked us like to write the general rule for the amount of cubic yards of sand. So this was our general rule, right? Back here. So it's kind of like, oh, I want to know where this derivative equals 0. I want to know where y prime of t equals 0. And if I took the derivative of the left-hand side, this y of t would turn into y prime. This is just a constant, so this would go to 0, go away. And the derivative of an antiderivative, oh, isn't the derivative of the antiderivative just the function by fundamental theorem of calculus? I mean, these boundaries are normal. This is a single variable on top. This is why this needed to be t and this needed to be x. So wouldn't the derivative of the definite integral from 0 to t of s of x minus r of x with respect to x just turn into s of t minus r of t? Oh, so y prime of t is really equal to s of t minus r of t. The sand coming in minus the rate of change of the sand going out. If you go to y3 and you store in y3, this is y sub 2 minus y sub 1. And you can use like your alpha trace to do that. Okay, so see how Mr. Herney did that? That's why you really need to make sure like you label which one you store where at the very beginning, so you don't ever store anything backwards. And besides just that, we also want not only where this equals 0, but switches from negative to positive. So
I also deselected y1 and y2 so it won't graph those.
Yeah.
So you just go over to the equal sign, like on top of the equal sign, you hit enter, and it will not be highlighted anymore.
And so you guys, this is why I always start with accumulation on this sandy beach problem, because like the kids at Palisade and Fruta never know how to do any of that on their calculator. And I'm not saying that you guys always know at the beginning of accumulation how to do that either, but when I'm showing it, like you know how to do alpha trace, you know how to do alpha y equals to get a fraction, like you know how to run math 9. So some of like those extra little skills, like you're better at. Notice we also set the window. I mean, they're telling you the time is 0 to 6, so set x min at 0 and x max at 6. And really, if we want to know where this equals 0, we're looking for x-intercepts. So we might as well just make our y min and y max small. So I did negative 5 to 5. And we want to find an x-intercept of that. So there's the graph. It is below the t-axis right now. Da, 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 da. Look at that. There's only one spot where it switches from a negative first derivative being below the t-axis to a positive first derivative being above the t-axis. So Mr. Herney is going to find the 0 using the second trace button to go into the calculate menu for me. And this is an intermediate step. We can't round this, so I'm leaving a lot of space so I can have all my digits here for that time frame with all of the digits written out. So we don't get our final answer wrong because we rounded too early. So you should get, when you do that, 5.1178653. And if you have a color calculator and it doesn't give you quite that many digits, it's at least going to give you those first 5.1178. It might give you a little bit more. And as long as you at least have the first 5 correct, it shouldn't throw off your final answer. But I have seen it, if you round this too early, it throw off a final answer. And if you don't have 3 digits correct, it's wrong. If you round to 2, it's wrong. It has to be 3 on AP. Okay? So it looks like we only have 3 potential candidates to test. Right? That's why we write down our candidates so then we can test them. So if you're like, oh my gosh, I don't know what to test them into. Yeah, you do. You wrote your rule for the cubic yards of sand at any time back here on part B. That's where you're plugging into. Oh, so y of 0, well, that would be the cubic yards of sand at time 0, which we already knew because that was our initial condition, which was 2,500 cubic yards of sand on the beach for the initial condition. So I'm looking for a minimum. Maybe that's going to be my lowest spot, maybe not. So if I try the other endpoint, which is 6, here we're finding the amount of sand on the beach, so the initial condition is part of it. So it'd be 2,500 plus the antiderivative from 0 to 6. Again, use your y sub 3. But I can't write y sub 3 here, right? That's calculator syntax. So I still would write s of t minus r of t. So I have, because it's the same for the whole entire time frame, you have sand coming in and you have sand going out the whole time, and you should get 2493.277. And that would be the cubic yards of sand at the ending time, times 6. Okay? So I'm kind of running out of space a little bit. I'm going to come up here. So way up here, the last one would be y of that 5.1178653, which would be the initial condition, 2,500 cubic yards of sand, times the antiderivative from 0 to that number, 5.1178653, of s of t minus r of t dt. And if you thought, well, those should be x's and not t's, well, now you have numbers going on. I don't think if you used x's or t's it would matter. So see how Herney kept all his digits, and then as he arrows over, he's doing y2 minus y1. I had stored that in y3, so I would have put y3 right there. Just so I don't subtract them backwards, right? You could do alpha trace and go down and pick y3. It should give you the same thing. So we get 2492.369. Cubic yards of sand in that scenario. So remember, after you test your candidates, you have to give them a conclusion. They're not going to know that you know what number is smallest out of those options. So actually in this case, they're pretty close. Like the initial condition and both of our other numbers are actually like all pretty close. But in this one, it is the potential local minimum spot that actually is the absolute minimum spot. Do not assume that it's going to always be this one. I've seen it be endpoints before, so you have to run the candidates test. So we would say something to wrap this up like, therefore, the time of approximately, here I would go ahead and round 5.118 hours and round to 3 places, is going to give the minimum amount of sand on the beach, and they did ask us for the minimum amount of approximately 2,492.369 cubic yards. So they're asking for both the y part and the x part in your whole conclusion. Sometimes they will just ask for the x or just ask for the y. Sometimes if they ask for one, it's typically the x, because sometimes the y can be messy to get. And so now we can just talk about points. Herney, do you have anything to add before we start points?
Not really.
Not really? Okay. So let's go through the points on this accumulation problem. So part A was 2 points. Did you set up your integral? So you did have to have the whole thing, the boundaries and the r of t and only r of t, right? And notice that in this case, it has nothing to do with the sand being pumped into the beach. It's just the stuff going out and removing. And then you got a point for your answer with your units. So you guys, if you didn't have the units, you don't get the answer. You had to have the units. So I guess one reason that they say integral is if you thought the initial condition had to be accounted for on part A, you could still get 1 out of 2, but you wouldn't get your answer because your answer would be wrong. If you forgot your units, you wouldn't get your answer point either. So I could see, as Herney and I are grading this one, oh, this is one that we're just showing you. But if we were grading this one, a lot of you missing that point because you didn't have the cubic yards. For part B, it was actually 3, which seems hefty to me. You got 1 point for your integrand. So did you know that you had to do the rate of change of the sand being pumped in minus the rate of change of the sand being pumped out? And you could set up 2 integrals or 1 big one. Okay, but that didn't even account for the 0 to t. It's just like the integrand, not the integral. So the integrand means the part after your integral symbol. You got 1 point for your limits. So did you know that you went for 0, because that's your starting time, to time t in general. And then you got 1 point for your answer. So that would mean, did you remember that the initial condition had to be considered at the beginning? You had to know how many cubic yards of sand were on the beach to start with before you thought about adding the stuff, what you would accumulate that was being pumped in, and the stuff that you would subtract out for the rate of change of the sand going out. Okay? And then I added the extra, like writing it in context part. So part C was actually just 1 point. Like, did you get negative 1.909? They didn't ask for units, so you didn't have to have units. Did you get the answer? I added the extra, interpreting it in context for other problems. Okay? So that was the part you had to get for that piece. The EBT, this is pretty typical, was 3. Usually it is 3 for EBT. So did you set y prime equal to 0? I remember y prime was just s of t minus r of t. So where was your rate coming in minus your rate going out going to equal 0 to find your critical point? And not only were we looking for a critical point, but also where that derivative switched from negative to positive. So that it could at least be a local min to even be in the realm for an absolute or global min. Another way to do that, I didn't show it, but you could have done where s of t and r of t were equal. So like put the one that you had in y1 and the one that you had in y2 and then find where they intersected. That still would have given you this same time of 5.1178653. So that's a different option. But this is kind of like more what we always do with EBT, even not on accumulation problems where the derivative equals 0. So that probably makes a little bit more sense. So 1 point was that you actually got this critical time of the 5.1178653. So this was kind of a soft point if you needed to do this. This was a bigger point if you could run your calculator to get that time. And then the last point was hard because you had to get the right answer with the justification. And the justification, you guys, is running through all of the candidates into the regular rule to see which one's bigger or smaller. So if any of that part in your justification of words was wrong, then you would have missed the answer point. Even if you kind of were on the right track, sometimes those answers, if they have an explanation or justification lumped with it, are pretty hard points to earn. Okay, so there's your total out of 9. So the one that you are doing for homework that's similar to this is also calculator active because it's either number 1 or number 2 from a totally different year. I think a year that's a lot closer to the year that we're currently in.
Still 13.
And make sure that you are getting set up and a lot of answers off your calculator. Use this one, go back and rewatch the video. We also did accumulation last week. You could go back and watch some videos of the accumulation from last week if you need extra help.